Hi everyone, welcome to the next part in our video series on AP Physics C, E, and M. Here we are in the second part of our unit on the electric potential, talking about the electric potential and its relationship to the electric field. So, some motivating facts that we'll address somewhat throughout the rest of this unit is that the electric potential of a surface is always constant if the surface is a conductor. So think about it. If that wasn't true, then that would mean that there's some potential difference between one part of the surface and the other. But if there's a potential difference, then that would mean that there's an electric field going parallel to the surface of the conductor and charges would move around. But wait a second. We're claiming that this conductor is existing in electrostatic equilibrium and charges would move around really quickly, so this would be a contradiction. So yes, any conductor, at least in electrostatic equilibrium, is an equipotential surface. And this is something to keep in mind when solving a lot of types of AP Physics problems on the AP exam, especially multiple choice questions where they'll say, like, give you two different conducting spheres that each have the same value of charge, and then when you end up connecting them together, charge might move from one to the other in ways that you wouldn't necessarily expect. But the point is, it must do so such that you end up getting the same electric potential on each sphere. So a capacitor is used to store charge for the flash on a camera, and it's able to discharge in a few microseconds. That is much faster than a battery can provide energy. In fact, for the defibrillators that help to reset heart rhythms, they use big capacitors for those so that they can discharge the charge in a very short period of time. But a downside of this is the large capacitors can be quite dangerous because they can transfer charge so quickly, and one once threw my dad across a room when he discharged it when he was younger. So connecting the electric potential with the electric field. So there are two different perspectives of how source charges alter the space around them. One is the electric potential, and the other is the electric field. And comparing the fact that the change in potential energy for anything that is affected by some sort of field is equal to the negative of the work done from initial point to final point, and that work is expressed by this integral, we can just divide both sides by charge and use the fact that potential energy per unit charge is electric potential. And force per unit charge also has a name. That's called the electric field. And this is a relationship that we have come across already in the course, and we're going to examine it in a little more detail from another perspective with a parallel plate capacitor soon. Now, also something to keep in mind, particularly for those of you who are interested in mathematics, anytime you have any conservative vector field, then it is possible to find some sort of potential that exists obeying this property. And by conservative vector field, we mean that by taking an integral along some path from point A to point B, you'll get the same result no matter what path you take, as long as your initial and starting points are the same. Or, likewise, taking an integral around any closed path is always going to give you a result of 0. That's the result of any conservative vector field. Anytime you have a conservative vector field, it is possible to find a potential such that taking the derivative of that potential ends up giving you the field, and maybe with a minus sign depending on how you think of it. So a common task is to use the area under the curve for the electric field to figure out the electric potential difference between 2 points. This often comes up as a multiple choice problem in the AP exam. Also, what they will often do is they will give an answer that just corresponds to the area, but the correct answer would be what you would get by putting a negative in front of that area, and we'll take a look at an example of this soon. Another useful integration trick that can sometimes prove helpful is setting the electric potential at infinity to be 0, and then saying that, okay, the change in potential between some point at radius r, position r, minus the potential at infinity is just equal to the potential at that position R because the potential at infinity has been set to be equal to 0. Now keep in mind though, in a lot of situations, especially for things like parallel plate capacitors, or I should say, well, just not so much capacitors, but sheets of infinite charge or infinite lines of charge, you can't set the potential to be 0 at infinity, or infinite cylinders of charge. So that's something else to consider, and you just have to treat those situations individually as they arise. In any case, some general recommendations when finding potential from a field. Keep in mind that it's a good idea to draw a picture and identify the point at which you want to find the potential. Call that position the final point, F, and then choose the 0 point, or at least an initial point where you know the potential. A lot of times that'll be infinitely far away, and call that position initial, or I. And then establish a coordinate axis from I to F, along which you already know or can easily determine the electric field in that direction. Sometimes you might do this multiple times. For example, go perpendicular to some axis and then parallel to that axis, depending on how the field is going. And then carry out the integration or the sum of integrals, depending on what the situation happens to be. So let's take a look at an example. The electric field in a region of space is given by E sub x is negative 1000 x volt per meter, and graph that over negative 1 meter to 1 meter, and then find the potential difference between negative 20 centimeters and 30 centimeters. So the linear graph is very easy. So there we go. Just have a graph, drew a straight line, labeled my axes in accordance. Now, in terms of finding the potential difference between the initial point and the final point, negative 20 centimeters and 30 centimeters, I used a trick. So I noted that the areas under this graph, and thus the potential differences between negative 20 centimeters and 0, and between 0 and positive 20 centimeters, are going to cancel because of symmetry. So the only thing that's going to be left is going to be the area of a trapezoid between 20 centimeters and 30 centimeters. Basically the area of a trapezoid kind of like this. So like this upside down trapezoid. So, well, I know the area of a trapezoid. A trapezoid is just a rectangle with 1 or 2 corners shaved off and moved somewhere else. So that means that we have the base times the average height, and since this height varies linearly, then the average height is just the initial height and the final height added together and divided by 2. So base times average height. And don't forget that I need to put a negative sign in front of this because the potential difference is the negative of this area. So now we plug in our numbers. The base from 20 centimeters to 30 centimeters is 0.1 meters. The one height is negative 200 volts per meter, another height is negative 300 volts per meter. And don't forget that there's going to be a negative on the outside that distributes through. So we get a potential difference, in this case, of 25 volts between negative 20 centimeters and 30 centimeters. Now, how do we create these types of potential differences? I mean, you know about batteries and everything. Those involve chemical reactions that provide energy necessary to do work to separate charges and move them around in a circuit. But a Van de Graaff generator also can generate a potential difference, in fact, a rather large one, I might mention. And by rather large, I'm talking about hundreds of thousands of volts. But fortunately, the current ends up not lasting for very long whenever you discharge it. Now, you can also plug something into a wall, which has a potential difference generated by a power station that works by various means. And back to our battery, something that we will often consider in this course will be something where there is an ideal battery that has a value of 0 for what we call the internal resistance, which we'll explore in more detail in the next unit. But in that case, the potential difference of the battery is the same as the potential difference across the circuit. And in any case, the work would end up coming from the difference in electric potential between the positive terminal and the negative terminal being created by the chemistry that's occurring in the battery. Now, you can also add batteries up So put one battery after another, such that the total potential difference will be just the sum of the potential differences of any of the batteries. I'll show you a diagram for that in just a second. Now, something called the EMF, the so-called electromotive force. It's an archaic term that implies like there's this force going on in the circuit, and to some extent there is a force on the charges because of the fact that there's an electric field due to the fact that there's an electric potential difference. But it's a misnomer in a lot of ways, and a lot of people just drop the term electromotive force, but they still use the symbol EMF and the cute little script E to symbolize it. But in an ideal battery, it's just the same thing as the electric potential difference for that battery. Now, what we mean by series and parallel, I'm going to show this on diagrams in the next slides, but when you have batteries that are in parallel, the electric potential difference doesn't end up changing, but the lifetime of the batteries is going to be longer. The lifetime of your device will be able to be longer. So in this situation on the left, I have a 5 volt, a 3 volt, and a 2 volt battery all in series. Well, these just add up together. So 5 plus 3 plus 2 is 10 volts. Now, some battery notation. Batteries are typically notated by having a long line next to a short line, and then they connect. The connecting lines and everything throughout the rest of the circuit, these act like wires. A short line is the negative terminal of the battery. The long line is the positive terminal of the battery. So, in this case, it is just a normal situation of 2 plus 3 plus 5. If I had, say, reversed the 3 volt battery and had the long line on the right side instead of the left side, then the whole electric potential of this whole thing would actually just be 4 volts. And that would not necessarily be a good idea unless my 3 volt battery happens to be a rechargeable battery, because I actually would be running current through it the opposite way to try to charge it up. So in any case, the net EMF of the system on the left is 10 volts. By the way, this zigzag line up here, this is the symbol for a resistor. And I should draw it a little neater than that. Generally, it's more regular than that, but that's a symbol for a resistor. But again, when you're talking about things that are in series, you can kind of imagine a little bit of a bunch of charge traveling around the circuit. And we always pretend that charge carriers are positive, at least most of the time when we're dealing with electric circuits. So in that case, our, quote, positive charge carriers would be traveling clockwise. Of course, what's actually happening is the opposite. It's negative charge carriers traveling counterclockwise. But there's no effect for most of the circuits we're going to deal with of the difference. So positive charge carriers traveling clockwise, well, they'd go through the resistor, and then first they would go through the 2 volt battery, then they'd go through the 3 volt battery, then they'd go through the 5 volt battery. So that's what we mean by in series. First this, then this, then this. On the other hand, in the situation on the right, imagine these charge carriers, they go through the resistor, and then they end up coming over here. Here they hit a junction. They have a choice of which path to go. They can either go through the top, or go through the middle, or go through the bottom. They have a choice. So that's the situation with parallel. It's either or with parallel. With series, it's first this, then this. So the geometry doesn't necessarily help you. For example, going back here, I could have put the 2 volt battery on the right side, the 5 volt battery on the left side. They'd still be in series, even though geometrically they appear parallel. So it's all about what's actually going on, logically speaking. So consider this situation. Determine the net EMF in this circuit. Give you a moment to pause the video. So assuming that you have paused the video and figured it out, hopefully the answer that you ended up getting was 4 volts. So just kind of imagine putting your 0 mark right here. So first you go up 2 volts because you've gone from negative to positive, so you've gained 2 volts. And then you've gone from positive to negative down this 3 volts. So you've just lost 3 volts of potential. So now you're at negative 1. And then you come up here, go from negative to positive, so you've gained 5 volts, and negative 1 plus 5 is 4 volts. So yeah, just beware of batteries that are set up the wrong way. So there we go. That's showing all of our work. Now, in terms of calculating electric fields from electric potentials, Again, we've already talked about this before, how you can just imagine the fact that a little bit of work is force times distance, so just divide both sides by charge, and use the fact that that work is being done by a field, so you get a negative sign there for the work being done by the field as the change in potential energy. But dividing both sides by Q, you get that your electric field is equal to negative dVds, where S is the little bitty path length along which the electric potential is changing. So yes, when there's an electric field, the electric potential is changing. That's kind of the point. So another way of looking at this with conducting plates, say you're going from 100 volts here to 0 volts. Well, I mean, the 100 volts is where you have the positive plate, the 0 volts is where you have the negative plate. So your electric potential is decreasing along the path in which the electric field is pointed. So the electric field points in the path of decreasing electric potential. So just going through this whole scheme again, force per unit charge, and then just -1 over Q times du ds, just thinking about the fact that force is the negative of the rate at which the potential energy changes. So it's another way of coming up with your electric potential compared with electric field relationship. And again, it's a negative sign, just like back in kindergarten physics when you had a negative sign in front of the derivative of the potential energy to get the force. In general, you might recall back in kindergarten physics that force is actually a vector, and that force vector is actually the negative gradient of the potential energy. So just making the analogy to E&M, we have that the electric field is the negative gradient of the electric potential. We won't really have any need of this in here, but it's good to keep in mind that, yeah, in a lot of cases, these things are happening in 3 dimensions. Now, what about equipotential surfaces? We mentioned at the beginning one of our motivating facts is that every conductor is an equipotential surface. Well, we need to think about this in a little bit more detail on equipotential surfaces in the imaginary framework before getting there. So let's consider 2 charges. I've used the charges and fields PhET simulation to model this situation, and I've just placed equipotential surfaces at units of 5 volts increment away from each other. Notice that they get tighter and tighter as you get closer and closer to the charge, until after a while I got tired of drawing them. So what that tells us is that the electric field strength is stronger as you get closer to the charge. What about the situation of a parallel plate capacitor? In this case, I did the same thing. I drew equipotential surfaces for every 5 volt increment between -110 and -120 and +120, and they are really, really tight in between the charges. So that's where the electric field is extremely strong, whereas the electric field is quite weak, relatively speaking, outside of your parallel plate capacitor, and in the ideal capacitor, the electric field is 0 outside. And then you can do that for other potentials as well, for example, the skull potential right here, etc. And again, notice that the electric field lines get really scrunched up once you get close to your charges. So we've already mentioned that the work done by a conservative vector field is always independent of the path, or at least the integral along a path from point A to point B in a conservative vector field is independent of the path. Well, since the electric field is a conservative vector field, in other words, it obeys a conservation law, conservation of energy, that means that the change in the thing related to that conservation law, that is the energy, is independent of the path that you take. Well, that is quite useful, and that's something that we're going to be coming back to in many situations. So think about just back to the gravitational field. Well, the work that you do if you go straight up the hill is just mg delta y. So the work done by the gravitational field is negative mg delta y if you're increasing your height. And similarly, if you are increasing your electric potential, the work done by the electric field is going to be negative. So here's another illustration of this path independence of work. In this case, the equipotential surfaces let us see where certain areas have a certain electric potential. In other words, everywhere along this kind of circular region has the same electric potential. And everywhere along this almost figure-8 region has the same electric potential, though it's different from what's on the circular region. But still, the change in potential energy from point 1 to point 2 is the same, regardless of whether we go along path A, along path B, or along path C. Notice that in the case of path C, I've moved along the region to a different spot, and then gone over, and then moved back. And the fact that I've gone forward and then back along equipotential surfaces tells us that the work done, and thus the difference in electric potential energy, and thus the electric potential difference, is the same whether I'm on any point on this figure 8 compared with any point on the circle. This itself brings about a very important law called Kirchhoff's loop law, or Kirchhoff's loop rule. You must memorize this. Going back to this picture, I could start at point 1, go along path C, get to point 2, and then come back along path A, or along path B, or along any other path that would take me back to point 1, and the change in electric potential would be 0. Now, in some cases, that could involve a number of steps. For example, how about from point 1 out? Well, there would be some change in potential there, which in that case actually is 0. And then, how about from this point over here to this other line over here? That's a different change in potential. And then this other line over here to this part of the circle over here, that's a different change in potential. And then from here down, that's another change in potential, 0 in this case. And then say back along path A, well, that's another change in potential. What Kirchhoff's loop law is telling us is that the total of these changes in electric potential is 0. So it's something that absolutely must be understood. It makes sense too. If you start at the top of the hill and you go snowboarding down to the bottom of the hill, and then you climb back up to the top of the hill, your change in gravitational potential energy and your change in gravitational potential is 0 for your net change. The sum of the delta V's along your loop was 0. So turning that part of the picture into a circuit, we could have, potentially, no pun intended, something like this, where we have a battery, and from the battery, there are 3 possible routes any charge could take. It could go through this resistor down here, or it could go through this resistor up here, or it could go through this thing up here where we have 2 parallel lines of equal length. Parallel lines of equal length are called capacitors, or at least that's the symbol for capacitors. Capacitors are devices that store charge, and we will talk about those in more detail in the next video. But in this case, notice that the 2 resistors and the capacitor are all in parallel. So no matter what path I take, as long as I start at the same spot and end at the same spot, my total change in potential is 0. For example, if I start just to the right of the negative terminal here, I end up having a gain in potential here, and then let's say I just go up along this red route, and then I go across this resistor, and then I come back to where I started. Well, Kirchhoff's loop rule says that the total change in potential must be 0. So whatever gain in potential here that I had from the battery must be a drop in potential going across the resistor. When current flows through a resistor, there is a drop in electric potential in the direction that the current is flowing every time. And also notice that the same thing would happen up here in this capacitor. In this case, there would be a gain in potential going through the battery and a drop along the capacitor. We'll have more to say about that later on. Now let's talk about conductors and electrostatic equilibrium yet again. So we mentioned at the beginning that conductors must be equipotential surfaces, because if they weren't, there would be electric field lines that are parallel, or at least have components that are parallel to the surface, and therefore the charge would be moving around, because that's what electric fields cause charges to do in when they can move around, and they do move around in conductors. That's why they're called conductors. But if the charge is moving around, it's not in electrostatic equilibrium. So, and generally speaking, electrostatic equilibrium is restored very quickly when a conductor is subjected to a quick change in an electric field. So any electric field lines must always be perpendicular to the surfaces of conductors. And thus, since there is no parallel component of that, everywhere inside the conductor, including the surface, must be at the same electric potential. So, something that you can hopefully convince yourself of is that, let's say you have a sphere of radius r, well, the electric field there is going to be kq over r squared, where q is the charge that's on it. The electric potential there would be kq over r. So, if we call that electric potential just V naught, then the electric field at the surface is just going to be V naught over r. Well, given that fact, and given the fact that V naught is the same everywhere on the surface of a conductor, what that means is that if you make the radius of curvature smaller, like say near corners and stuff like that, the electric field there is going to be larger. In fact, as it turns out, because of the fact that the electric field there is larger, the power law relationship with which it's larger is such that the actual surface charge density here ends up being larger as well. In fact, the surface charge density turns out to be inversely proportional to the radius of curvature. So you have more charge at the pointy ends, and you have stronger electric fields at the pointy ends. This leads to a popular misnomer about lightning rods. Some lightning rods actually do have sharp points to create strong electric fields. Now, if you hang around on shady street corners and start reading shady textbooks like our own, this is a joke, I love our textbook, you might end up getting the impression that lightning rods work by draining charge from the surface and out into the atmosphere so that there doesn't end up being a lightning strike. Well, that is in complete contradiction to this situation of the lightning rod often getting struck at the top of, say, the Empire State Building. I think it gets struck something like 200 times a year. The whole point of this particular design is actually to create that very strong electric field to attract the lightning there so that it gets discharged on the conductor and thus grounded instead of into the rest of the building. So that's the whole point about that, no pun intended. But you can also have spherical lightning rods. In fact, when I was in China, I saw a number of lightning rods that were actually spherical in nature. And in those cases, they simply stored a bunch of charge to create a big electric field over a large area and thus attract the lightning there. Either design actually ends up working quite effectively. So whether it's a point or whether it's a sphere or a ball or a bell, they all end up working quite well for attracting lightning and grounding it so that the building itself ends up being safe. So this leads us to the idea of capacitance, the ability to store charge. We saw a capacitor in one of our quick little example circuits, and in the next video we're going to examine what these things are in more detail. And I'll see you then. Thank you for watching.